course, we'll cover the rest of the key parts in the next couple of slides as well. We'll give a clear definition then. I see someone in the chat has their hand up as well. They also gave us a definition, which I thought was very, very good. I'll read it out now. Machine learning is a subset of artificial intelligence focused on algorithms that enable systems to learn and improve from data without explicit programming. AI encompasses broader concepts, including reasoning and decision-making, while ML, or machine learning, specifically deals with creating models to identify patterns and make predictions from data. So you're very much on the mark. The key point here, the key distinction, is that machine learning makes heavy use of algorithms and statistical data alongside the implicit programming as well. So if we look here, and once more, I'd just like to have a couple more disclaimers. This is our very first run through of ExeAI, so of course, we're trying our very best. And I always also encourage hands up at any point. If there's any questions or queries on your mind, please raise, and we'll always be there to help. It's not strictly like a lecture. It's more of a fun lecture. you can feel comfortable and relaxed here. So yes. Right. So the definition here given in the chat was wonderful. We have it basically from a sort of paraphrase quote here. Machine learning again focuses on algorithms which help computer learn from data without explicit programming. Now, this term, why it was used in the chat and why it's being used here, is actually very important. It's actually, again, a paraphrased quote from an American computer scientist. His name is Arthur Samuel, and he is a real pioneer in the realm of machine learning in the 1950s. To gain a deeper understanding of what machine learning is, I actually think it's very important to first cover what learning is in a vacuum, the meaning of learning. And for this, I actually have a quote. This is a quote by a Nobel Prize winner, Herbert Simon. He says, "Learning denotes changes in the system that are adaptive in the sense that they enable the system to do the same task or tasks drawn from a population of similar tasks more effectively the next time." So you're going back over and over again, and you're changing some of the variables, changing some of the fields and the degrees of freedom, which is a term we will cover in our next lesson, to achieve a better result, a better, more accurate model that you're creating to learn from data. I'd just like to ask for those experienced in programming, Excode attendees may jump in for this one. What cornerstone of programming do we use to achieve a result after a loop of successive goes? What do we call that loop? What cornerstone of programming do we use? Yes. Iteration, yes. We're using iteration. Sorry? Iteration. Shall I go through iteration? Oh, no, sorry. So yes, we use iteration. Okay. So artificial intelligence is an area of computer science where the goal is to enable computers and machines to perform human-like tasks and simulate human behavior. So that's how AI differentiates itself from machine learning. Again, the chatter in Microsoft Teams, and you're very much on the mark. It's a subset. AI focuses on the whole deal of human behavior and whatnot. Machine learning focuses on the statistical, mathematical aspect behind it. So as you can see here, machine learning, down to its core, it's a blending of computational algorithms and mathematics to create whatever that is. And as you see on the right, we'll cover this briefly, and we'll cover this in greater detail in another lesson. We have an example of wrong classification. So this is very clearly a cat, but it's been given the wrong label of dog. And if we sit tight for a bit longer, we can go through why that is and how classification in its own right works. So what's important to note is that there are actually three main types of machine learning. The first is supervised learning. So supervised machine learning's main draw is mapping an input to a labeled output. We know what the output labels are. So in some respect, we as the human, when we are training this model, know what the output should be. So if I were to go to the whiteboard really quickly. Oh God, goodness. I think I stopped broadcasting for a second. Sorry, thank you so much. Yes. Thank you so much. So we have an input. Pardon me, drawing with a mouse is never easy. I always like drawing with a drawing pad whenever I do digital drawings. So we have an input, X. And when put through, we expect an output of label Y. So we can have multiple different labels that we can fit X to create and discover a pattern amongst the data. So let's say here, we have some apples and we have some bananas. Supervised machine learning is actually very beneficial in image recognition. So once it sees something, it can fit a label to it. Say we have two labels, apple and banana. Let's say we can see now this is being identified under the label apple. So it gets sorted with the apples. And I understand it's very difficult to see for both the digital viewers and the local viewers, but I'm trying my best here. But this would be a banana, and with image recognition, a trained model can identify this under the label banana. So it'd be placed here. It fits it according to a label, an expected label. We know what the outputs are. So as we see here, and another example of where supervised machine learning gets used in image recognition, we have three labels right here. So a bot would be able to tell from this image that it's a cat, that's a dog, that's a lizard. A key thing to note is that if the model has not been given all the labels, it cannot identify everything correctly. Let's say the model was given these three images, but it had no distinct label for a cat. It would likely be placed under dog or lizard, which is wrong, evidently. So some key examples of what machine learning, supervised machine learning can be used for. Spam filtering with like recognizing certain words, image recognition, text-to-speech, and so on and so forth. Now, unsupervised machine learning is another very popular, sorry. Oh, goodness, yes, thank you. How do I?
It's a bit tricky, yeah.
Oh, there we go. There we go. So unsupervised machine learning is where we do not exactly know what each output Y should be. We don't have any labels basically, but from the data that we are giving this trained model, it can then form patterns that we can draw around and form clusters. So unsupervised learning is useful for taking seemingly unrelated data and forming them into clusters of data that can then be identified. So on my previous example, where we put each apple with a label called apple, we don't have a label called apple anymore. This is its own individual item now. Let's place this around here. Can everyone see that? Sorry for people at the back. But now we have another apple. We don't really have a label to put this under, but we can see that these two are functionally and well, appearance-wise very much related. So you put them in the same cluster. That's how we identify a pattern amongst a piece of data using unsupervised machine learning models. And in a similar vein, bananas are very much distinct from apples, so they'd go in their own cluster. So, and in another example, going back to the pets idea, we don't have a distinct label, but we then, when given new pieces of data, it will then group the similar ones to those clusters, to those distinct data points, and it will draw around them. Right. So this last one is actually used a fair bit less than the other two. This is reinforcement learning. Reinforcement learning is actually a much more computationally dense and expensive model to use, and that's actually the fact why that's actually in fact why it's not used as much, because a key cornerstone alongside the paradigms and structures like iteration and conditions is very important for us to have computationally inexpensive programs that run fast and do not take up too much storage. So with reinforcement learning, we're giving the model wrong and right data, and based on its right and wrong predictions, we are either distributing penalties towards that model or benefits towards the model. And that way, the machine learning model can make better and more accurate predictions going forward. Who here plays a lot of video games? Who here likes speedrunning video games? Does anyone familiar with speedrunning games? Like where you that's a very niche term. I understand that's a very niche term. Where they have to like learn how to play the game as fast as possible. Yeah, sometimes some programmers will use what's called a tool-assisted speedrun, where they'll get a machine learning model to be placed into this the situation of the game, and based on its surroundings, it will make the correct condition, it will make the correct movements for the player character, and it will learn from benefits and penalties whether or not it made the right decision. So that next time around, next run you play, next level you play, it will learn better how to complete the level faster. Does that make sense? Yes, it's very exciting stuff. But also very difficult. I'm seeing now in the chat, yes, Temple Run Subway Surfers, yes, this guy gets it. Yeah, but again, it's after each run, and after each run, you're learning something new and more. So that involves a lot of runs and a lot of permutations of data, which is why reinforcement learning is not used as much. But it is on the come up. It's getting more and more popular. See here, optimized models in Trackmania for the fastest bot racer. Oh, we got some good discussions in the chat now. This is interesting. But yes, it's in essence reinforcement learning. Image on the right. That's not how you train a pet. Don't learn from that. But in essence, reinforcement learning is actually derived from behavioral psychology, where consequences are derived, and the notion of a reward is also derived from those consequences. So based on the model's actions, it will receive different outcomes and different rewards. But again, it's a much more complex model than supervised and unsupervised. And in fact, the main paradigm of machine learning we'll be learning mostly here is supervised. So supervised, I think, in my opinion, is the best to learn. It's the most relevant right now. It has a heavy dominance in today's market, responsible for 99% of the economic value generated by machine learning. And within that subset of machine learning, we actually have two more. There are two types of supervised machine learning. Remember, supervised machine learning is taking an input label, input X, and mapping it to an output labeled Y. We know what each label output should be. Now, so within classification, so this is one type of supervised machine learning, classification. Do you remember when I had the apples and the bananas, and I put them into under label apple and label banana? Functionally, apple and banana are both classes. We have a class for apple and a class for banana. They're both distinct in that aspect. Any raise hands again, any programmers? Any object-oriented programmers using that paradigm? Nice, nice. Essentially, you're fitting it into classes that have their own characteristics. But in this aspect, we're looking specifically at the object in relation to other objects to derive a pattern. So here, one type of classification is multi-class. There are multiple different classes, usually spanning 3 or more classes that an object or a piece of data can be. So we have hot dog, burger, Coke. It can either go into one of those 3, and a model will correctly identify one and put them into that place. Conversely, we have binary classification, where it's one or the other. So in this example, you will have noticed I used apple or banana. You may recognize that that is in fact one or the other situation. So with binary classification, it's one or the other. So up above is hot dog or not hot dog. Feasibly, you can make this apple and not apple, and it would still have the same result. That would be in its own right binary classification. The second type is regression. So the reason why we have 2 different types of supervised machine learning is that they're both used to compute and model different types of data. Classification, as you saw, it can be one or the other. It's discrete. Discrete meaning there is no value in between one. You can't have a burger Coke, basically. Regression looks at continuous values. Anyone here do A-level maths? A-level maths, and obviously we had the statistics module in A-level maths. It was a real doozy, but I actually often remember times writing my own regressions and calculating them out. Thankfully, we now have programs for that, so that's wonderful. That's amazing. We're looking more at linear regression for the rest of this this lesson here. Linear regression, for anybody who's taken mathematics or is currently taking mathematics. No worries, no worries. Linear regression is just a straight line that models the data. It measures a linear trend between an input against an output. So let's look at this example here. We have along the bottom house size in square feet and the price of the house in thousands of dollars. Can someone here, just by looking at it, describe the correlation between the two, just by looking at it, if possible? Yes, yes, it's very much displays a moderately strong positive correlation between square footage and price. Even the untrained eye can look at that and recognize what that can be. But it's important we have a regression algorithm for that, so that if we actually want to predict an accurate house price within this range of data, we are able to, and then make educated guesses based off of that. And in this instance, make more money off of that, which is pretty great. So now here, say we wanted to find the price of a house based on the size in square feet, and we wanted a house with 1,250 square feet. Looking at this regression that's been calculated, we can then measure along the sides. Measure along the sides and see that it would be $220,000. Now that we've seen that regression, we must best learn how it's actually made and how we actually come to a conclusion like this. So now you're probably seeing a lot of these symbols, a lot of these equations. Please don't panic. You will not be having to outright calculate and write down these equations. Okay. libraries in Python and in the notebooks that you'll be using do this stuff all for you. But back in the day, you might have had to, the people back in the day, they walk so we can run. And that's quite brilliant. So when making a linear regression, it's important to first understand what a linear line, how that equation is made. It's y equals mx plus c. Anyone from A-level maths may remember that. May look here. We are using different, it looks slightly different. It's important to note that when we're using y equals mx plus c, like labels like y, m, and c being the output, the gradient, and the intercept respectively, are all at the end of the day variables. For those who'd like to know a bit more, like understand more about what a variable is, it's basically like a wrapped box that has its own characteristic based on a starting off object, in a sense. For more information on what that can be, you can find me during the lab practical, and I can talk to you more about that. Oh, or put your hand up in the chat as well. I can do that as well. But yes, no explicit programming needed from this. But it is important what each thing, what each aspect of this function actually does and why it's needed. Now, as you can see here, we have a test regression straight line here to measure this data, which is looking seemingly positive. And we're seeing these lines going straight down from it. This measures the distance between each data point that actually exists and the prediction that we are making. This distance, this vertical distance, is called a residual. And it's actually used in making our cost function. Now, cost functions are extremely important because they are actually what defines for us a correct model. A cost function in essence is an enumerated value or a value given a number that basically defines how accurate your model is. So the goal is to minimize this cost function right here. Again, ignore the rest of this part here, what the equation actually is. Let's look at j of theta 0, theta 1. Theta 0 and theta 1, this is actually the Greek alphabet here, theta, represents the intercept and the gradient, respectively, of our model's line. And what we have right now is the goal of minimizing that to the lowest possible. We've got a question here. Is a cost function similar to r squared and h? Residuals are actually calculated, I believe, using r squared. Yeah. So yeah, you are correct in that aspect. Yeah. That's how a residual is. So if we look here, inside these brackets here, we have our lines prediction against what the actual prediction is, and it's squared. That is a residual. So if I were to type it in the chat, yes, you see it now, yeah. So the residual, or r squared, being the distance between the two, is this part right here. And we want to minimize that distance overall. That is how we minimize the cost. The reason why it's called a cost function, the best way to remember it, is that you're trying to reduce the time loss or the time cost, that is, of making a wrong prediction. So having it be less expensive is actually better because you're making more accurate predictions. So again, back to our example of size in square feet and price in thousands. We have this linear regression right here. Again, in the structure of y equals mx plus c, but now we're using letters to better distinguish what we mean by each thing. So w, where gradient once was, is the weight or the slope. B is bias or y-intercept. Before I go any further, does anyone have any questions in the chat or want to put their hand up? Wonderful. I'll further just divulge on what bias really means. So say you have a trend that's being met in a linear regression, but the intercept does not start where you want it to be. You can just shift the bias accordingly to get the gradient matching with where the intercept would start. So let's look here by what I mean. Here we have 3 examples, and I'll be linking this back to our house price example afterwards. But in this first one, we have a weight of 0 and a bias of 1.5. That means that the intercept is 1.5 and the gradient is 0. So no matter what value you have, it will remain at 1.5. Let's link this back to the house price example. Why is this unlikely? Why would you never see this regression being made for house prices? For the first one, yes.
Same prices for like the.
Square feet increases.
Yeah, so that there's a variable element to it. There's clearly a correlation being made, and what's more is when you're applying that to reality, it's kind of unlikely to expect that the price of a house will be fixed across the board, regardless of square footage. Looking at this one here, we now actually have a gradient, so somewhat of a positive correlation, but the intercept is 0. So it goes through the origin. Why might this be frowned upon with our example? Can we, yeah? Exactly that, yes. First and foremost, you will not be getting a house for free, and also not be getting a house with 0 square footage as well. So yes, very good. Of course, in this one, again, it starts off at 0, which begs the change in scale, of course. But we actually have a non-zero intercept and a non-zero gradient. So we're seeing a much more likely correlation being made. Again, shy away from this giant, scary looking algorithm. You'll never have to complete it manually in our course. But there are some aspects that I think are very noteworthy to look at. So this part right here, 1/2m. So each residual, as you previously discussed, is this part here. Each expected y minus actual y squared is actually totaled up and divided by 2 of m. M is another variable, and that means m describes the number of training examples. So training example is 1 entry of data. Say you had a data set with 50 entries in it, m would be 50, simply enough. And averaging and squaring here is how we get a positive residual, because if we have a lower expected y than an actual y, we'll get a negative value, and that messes with the overall like cost function. But not only does it actually help make it positive, it's actually used to help like make edge cases and anomalies stand out further from actual data points that make sense. So a key thing to note is that with any piece of data, there will be edge cases and anomalies that will just not make any sense. Basically, squaring helps in closer and more accurate prediction. So it helps with accuracy, and also differentiates the larger, more out there, more overzealous answers that shouldn't really be there. And again, having a small cost function means that our model is fitting the data very well, and a large one means that we're actually getting very far from our actual values. So how we actually go about finding a better values, better parameters for our cost function is by using something called gradient descent. Now, what this visualizes here is the height being the actual like total cost function. So when it's higher, it's actually much worse. and lower being where we actually want to be, where we're having a low cost function. Of course, we don't know what this graph looks like before we go into making, pardon me, our cost function. So how it sort of works is I want to all visualize with you. We're standing at the top of a very hilly surface, big mountain, and that's where we're representing our starting point to be. We are now trying to find within a set range the steepest possible descent down from where we are. And once we do, we find the steepest, we go down. Then from there, we find the steepest descent and go down from there, gently trickling down further and further. Another question that I don't want an answer to, it's a rhetorical, something to keep in mind. Does the steepest descent mean the longest descent down? Depending on the distance you're traveling each time, because it's a fixed distance each time you're traveling, it might not actually mean you're reaching the bottom the fastest, or the general lowest point the fastest. Now, these lowest points, they can be referred to as various things. Of course, this is where we want to reach. They can be referred to as valleys or troughs. I prefer referring to them as troughs because that's how I find it more easy to remember. But yes, the goal to reach the. Pardon me, my mic is fallen. I also noticed the microphone machine slipped out as well. Yeah, okay. Sorry about that. Pardon the technical difficulties. Let me just. Okay, hold on a minute. Take 5.
I just want to say, these concepts, I think, are much harder to explain than just general coding concepts. Like, generally, please applause the speaker because it definitely merited. It's not easy to do this.
Thank you so much. Thank you. Hello? Wait, is it right? Okay, good. Thank you so much, and thank you for all your patience as well. Yes, I'm actually a student for the record. So yes, I'm trying my very best, and hopefully each week I can bring you consistent knowledge that you can walk away happy with. And I'll be holding it in my hand from now. No more slip-ups, because that was terrifying. I would have walked around much more. So yes, if you're wondering how we actually get atop that slope, how we actually reach the hill where the cost function is the highest, we actually just take values of the gradient and the intercept we want, and then adjust accordingly after each cost function we derive, find, until we reach a minimum. And again, you keep calculating that steepest descent and reevaluate afterwards. So like how I described, you're going down the hill, finding the steepest climb down. Once you reach each point in your gradient descent, you are then going to find whether the steepest climb down from it is there, what values of W and B there'd be. But there are a couple of problems. In some cases, as I go back and see, we will reach a minimum, but it won't be the lowest minimum. This is what we have. This is what we call right here, in cases A and B, the local minima and the general minima of C right here. Ideally, we reach this lower minimum, but if we don't try multiple times from multiple different locations on this plane, we might actually reach what we think is the lowest point. But that's in fact not the most efficient and not the most accurate either. So we start at different points on the cost surface. This plane I described here is called the cost surface, and it's also looking like this as well. Is everything I'm saying making sense so far? Does anyone have any questions? Is the chat okay? I think we're all good. Yes, just have to check. It's a very difficult concept to get quite right. So I'm hoping that everyone's finding that okay. So yeah, if it stays in one value, you won't find any other values. So the importance of trying again and again is what's necessary here. You might be wondering, with reinforcement learning, I sort of blew past it, saying that it requires so many tries. As you can see with GDA or gradient descent algorithms, it requires much less because there are far fewer highs and also fewer lows to just work through and find. So yes. Now, another key thing to highlight about gradient descent algorithms is that they can be done in two ways. Randomly, where you randomly find a height and randomly pick values to go down from, pick values of the gradient and intercept to go down from. This is called stochastic gradient descent, or stochastic even, is another word for random. We also have calculated gradient descent, where you're going by a set value each time, and it's far more methodical. Typically, the best way to find the general minima is by trying multiple times and using a mix of random and calculated values to find the general minima. Now, a problem that you can have with a general learning, with a learning rate in gradient descent algorithms, like how I described, where the steepest descent might not always be the longest descent down. That's because you're using maybe either too short or too long of a learning rate. A learning rate describes the difference in jumps or steps you take down the hill each time. Finding the right learning rate is important because, as we see here, if we have a learning rate that's too small, look how many jumps we're making down that hill. It's almost assured we can find that bottom, the trough right there. But if it's too small, like if we can see here, 0.000001, there's tiny steps, slow convergence. We can find the trough that we want, ideally, but it would take so long. And as we had described beforehand with reinforcement learning, that would be computationally expensive and inefficient, and in the long run, we actually frown upon it. On the complete opposite end of the spectrum, we actually have a learning rate that's too big. Now, a way I like to visualize this is instead of walking down that hill, you're at the top with a golf club and a golf ball, and you're just playing a game of hilly golf. Driver in hand, and you're sending it onto the other side of where the hill is, of that valley. And you're sending it back and back and back again. You're not using any smaller values to change the values of the gradient and the intercept by. So you're just going to keep going back and forth again and again. You are decreasing over time, but there are two problems. One is inaccuracy. If you make too many big bounds, you won't actually reach the bottom where the minimum is. Another problem is that there's actually a chance you might actually reach another trough you're not supposed to reach. Say you're on the right, and you use even a larger value perhaps, you can probably go into the next valley over and not reach what you're intended to find. So it's inaccurate and can actually have increases instead of decreases should it spill over into another valley. So that's actually the end of this particular session.